This is Dr. M. Vairalashmi, Assistant Professor of Chemistry, V.V. Vaniya Perumal College for Women, Virudhunagar. Today I am going to discuss about application of Orgel diagram to the electronic spectrum of octahedral complex, especially for D7 octahedral complex. Let us see. First of all, what is an Orgel diagram? It is a qualitative energy level diagram which is used to predict the electronic transitions of transition metal complexes. It is used to interpret the weak field or high spin transition metal complexes. It cannot able to explain the low spin complexes. This is the limitation of this Orgel diagram, and it explains the spin allowed electronic transitions. I already told it is a qualitative diagram, so it is not able to calculate the exact energy of the system. Only it is possible to calculate the relative energy of any system, that is high spin complex only. Next, crystal field splitting in octahedral complex. Crystal field theory explains there is an electrostatic interaction between the ligand and the central metal ion. Due to this electrostatic interaction, the degeneracy of the metal ion will be removed. So it will split into T2G and EG set. Okay, here this is an octahedral complex. So 6 ligands approaches the central metal ion along the X, Y and Z coordinates. Due to this attraction between the ligand and the central metal ion, the degeneracy of the central metal ion will be removed. So it will be split into T2G and EG. Okay, so T2G sets having lower energy level and EG sets having higher energy level, because in the octahedral field this EG orbital, that is the orbital consisting EG set is dz square and dx square minus y square. So these two are axial orbitals. So these loops are present along the axis. So it will get more repulsion than the T2G orbital. So EG goes to the higher energy level and this T2G having lower energy level. Okay, so the energy difference between these two, T2G and EG, is nothing but delta naught, or otherwise we are call it as 10 dq. Del naught is nothing but crystal field splitting energy. Del, the symbol del represents the crystal field splitting and naught represents the octahedral field. Okay, so the energy difference between these two is nothing but crystal field splitting energy for octahedral complex. So this is an Orgel diagram for D7 octahedral complex. This F term is split into two sets. It split into two triplet state and one singlet state. Two triplet state is nothing but T1GF and T2GF. These two are triplet state, and this A2GF is a singlet state. So F term is split into two sets, two triplet and one singlet. And then this P set doesn't split, it remains act as a triply degenerate state, that is T1G state. Okay, so here because of the same symmetry of the two T1G state, because of same symmetry of these two T1G P state, there is an interaction of these two orbital. Due to this interaction, it lowers this lower energy state T1G and it increases the higher energy level, that is A2G. Okay, so due to the same orbital interaction, it lowers the lower energy state and it increases the higher energy state. Okay, and then the interaction of these two lines, depends upon the Raka parameter value, that is beta. So this crossing is prohibited by non-crossing rule, which states that the state of same symmetry cannot merge each other. So this is non-crossing rule. Okay, so this is an Orgel diagram for D7 system. So this is an energy of the T1G state, that is T1G F term is destabilized by the amount of minus 6 dq, and this T2G F is stabilized by the amount of plus 2 dq, and similarly this A2G F is stabilized by the amount of this 12 dq. Okay, next this is an example for this D7 octahedral system, cobalt hexaqua complex. Here central metal is cobalt. What is the valence electron of cobalt? That is 9. Here cobalt is in plus 2 oxidation state. So 9 minus 2, 7. So cobalt 2 plus having 7 valence electrons. So this system is an example for D7 octahedral complex. Okay, so this complex exhibits 3 absorption band nearly at 8000 waves per centimeter, 19,600 waves per centimeter, and the third absorption occurs at 21,600 waves per centimeter. So these are the transitions. Okay, so the first transition is due to T1GF to T2GF, and the second transition T1GF to A2GF, and the third transition is T1GF to T1GP. So these 3 are the allowed electronic transition for this system. Okay, so the ground state term is F4. Okay, so the ground state term is F4. The same spin multiplicity 4 is also exists in the excited state term P4. So this is an example for D7 octahedral system. Okay, so now we can calculate the 10 dq value. That is, what is 10 dq? Crystal field splitting energy. Okay, so we have to find out. Here it is a first electronic transition, new one, that the value is 8000 waves per centimeter. Here we can write the energy difference between the first transition T2G F minus T1G F, that is equal to 8000 waves per centimeter. Okay, here the energy of this T2GF is nothing but plus 2 dq. T2GF energy is plus 2 dq, and the energy of this T1GF is nothing but minus 6 dq. So we can substitute these two values in the equation. So we can get the value of dq as 1000 waves per centimeter. So obviously 10 dq is equal to 10,000 waves per centimeter. So in this way, by using the any one of the 3 transition value, we can predict this 10 dq value. So what is 10 dq? Crystal field splitting energy. So we can found out, and the next we have to find out the beta value, that is nephelicity ratio value. So for that purpose we can compare all the 3 transition. So we can find a new one is equal to 8 dq. So this is already we can discussed, that is energy of T2G minus T1G is equal to 8 dq, and this is new 2, that is second electronic transition. Okay, so this is a second electronic transition, that is A2G minus here T1GF. Okay, okay, so nu 2 is equal to energy of A2G minus energy of T1G, that is equal to 18 dq. Similarly, nu 3 is equal to energy of T1GP minus energy of T1GF, that is equal to this energy of T1GP is calculated from the Raka parameter value. Here for a complex, the F and P terms are separated by 15B prime. For a free metal ion, the F and P terms are separated by 15B. So here we can discuss the cobaltic complex. So it will be 15B prime. Okay. So now we can calculate the B prime value from the third equation, that is nu 3 is equal to 15B prime plus 6 dq. Okay, here we can so this nu 3 is known, so is already the third electronic transition we know. So B prime, we have to find out the value B prime, and here 6 dq. So we have to find the value of this 6 dq. For that purpose, we just imagine this 2 nu 1 minus 10 dq is equal to 6 dq. Okay, so we can calculate new one as 8 dq. So 2 new one is equal to 8 into 2, 16 dq. So 16 dq minus 10 dq, if that is equal to 6 dq. So in this way we can calculate the 6 dq value. So by substituting this 6 dq in this equation, we can get B prime as 1040 waves per centimeter. So this B prime is nothing but interelectronic repulsion between the complex ion. Okay, so this is a beta, that is Raka parameter, that is equal to B prime by B. So this B is nothing but interelectronic repulsion between the free metal ion, that is it is a constant value, that is 971 for this cobalt free metal ion. So by substituting that value in that equation, we can found the value of beta, that is 1.01. Okay, from the value of this beta, so we can predict the nature of the complex. If beta value is less than 1, we can predict the complex should be covalent. Okay, here it is equal to, nearly equal to 1. It means that the complex should be ionic. So in this way, we can predict the crystal field stabilization energy and also this beta value, that is Nephlocytic ratio. From the Nephlocytic ratio, we can predict the nature of the complex, whether it is ionic or covalent. So in this way, we can predict the that is 10 dq and beta value for high spin transition metal complexes. Okay, thank you for watching.